Everyone, what's up? Welcome back to my tutorial channel. Daniel's here, and today I'm talking about lesson 8, John, Marginal, and Conditional distributions. And the lesson today consists of John distribution of random variable x and y, Marginal distribution of x from a John distribution of x and y, independence of two variables x and y, conditional distribution of y given x equal to little x, covariance and correlation coefficient, and moment generating function. So first, let's get start off with the John distribution of random variables x and y. We describe the probability distribution of two or more random variables together as a John distribution. If x and y are discrete random variables, we have f of xy is probability that x equal to little x, y is equal to little y. And this John distribution must satisfy. The John distribution should be between 0 and 1 because it represents for probability. And the sum, double summation of this density function respect to x and y is 1. In continuous case, the John distribution of x and y is between 0 and 1, and the double integral is of the John distribution respect to y and x is 1. Here, one thing you should notice, in continuous, we don't have probability x equal to little x and y equal to little y because for continuous random variables, the probability at a single point is 0. So keep this in mind. For discrete, to find the John distribution, we can use probability x equal to little x, y equal to little y to compute the John distribution. But for continuous, we need a technique that I'm going to introduce later. So next, cumulative distribution function of John distribution. If two random variables x and y have a John distribution, then the cumulative distribution function is capital F of x, y at the point little x, little y is probability that x less than or equal to x and y less than or equal to y. So here for discrete is a double summation s from negative infinity to x, t from negative infinity to y, the density function at the point st. And this is summation, double summation of s from negative infinity to x, t from negative infinity to y are probability that x equal to little s and y equal to little t. And for continuous, the cumulative distribution function is the double integral from negative infinity to x, negative infinity to y, fxy at the point at t, dt ds. And the John distribution is we differentiate twice respect to y and x. So here the technique to find the John distribution for continuous case is we find the cumulative distribution first, then differentiate twice, one respect to x and one respect to y. So that's the technique. Next, expectation of a function of jointly distributed variables. If h of x and y is a function of two variables x and y, whose John distribution is f capital Xy of xy, then the expectation of the function h of xy is defined as, in discrete case, is the double summation, and in continuous case we use double integrals. Next, marginal distribution from a John distribution of x and y. If x and y have the John distribution with John density and probability function fxy, then the marginal distribution x has a probability function or a density function denoted by f capital X of x. And the marginal function, the marginal distribution y has a probability function or a density function denoted by f capital Y of y. In discrete case, we basically summation the John distribution over r value of y for marginal distribution of x. And for marginal distribution of y, we sum up all the John distribution over r value of x. And in continuous case, we basically do the integrals instead of summation. To find the marginal distribution of x, we integrate the joint distribution respect to y. And to find the marginal distribution of y, we integrate the joint distribution respect to x. Independence of random variables x and y. Random variable x and y are said to be independent if probability space is rectangular. X is restricted between A and B, Y is restricted between C and D, and the joint distribution is f of xy at the point xy is f of x times f of y. So basically the joint distribution becomes the product of the marginal distribution. And the conditional distribution fy given x literal to x at the point y is simply the marginal distribution of y. Independence of x and y is also equivalent to the factorization of cumulative distribution. So when x and y are independent, not only the joint distribution becomes the product of two marginal distribution, but also the cumulative distribution also the product of two cumulative distribution. Conditional distribution. Remember, the conditional probability is probability A given B is probability of A and B over probability of B. So conditional distribution of y given x equal to little x is, in discrete case, we have f of y given x equal to little x is probability that x equal to x, y equal to little y over probability x equal to x. And in continuous case, we have f of y given x equal to little x at the point y is the joint distribution fxy of xy over the marginal distribution of x. Covariance between random variables x and y. If random variable x and y are jointly distributed with joint distribution function fxy of xy, then the covariance between x and y is expected value of x minus ex, y minus ey. And this is expected value of x minus mu of x times y minus mu of y. And this is equal to e of xy minus ex times ey. Variance of function of x and y. Variance of ax plus by plus c is equal to a squared variance of x plus b squared variance of y plus 2ab covariance of x and y. C is a constant, so we can ignore C when we calculate variance. And the coefficient of correlation between x and y is rho xy at the point xy equal to covariance of x and y over sigma of x, sigma of y, where sigma of x, sigma of y are standard deviation of x and y respectively. And note that this correlation coefficient is between -1 and 1. If the correlation coefficient is close to 1, then x and y have a positive linear, strong positive linear relationship. If the correlation coefficient is close to -1, then x and y have a strong negative linear relationship. If the coefficient of correlation between x and y is close to 0, then x and y have very weak linear relation. Moment generation function of a joint distribution. Given a jointly distributed random variable x and y with a joint distribution function fxy of xy, then the moment generating function of a joint distribution is mxy at the point t1, t2 equal to expected value of e to the t1x plus t2y. And the moment expected value x to the n, y to the n is we differentiate m plus n times. M time respect to t1 and n time respect to t2 of the marginal of the moment generating function, and take it at the point t1 equal to t2 is equal to 0. The bivariate normal distribution. Suppose x and y are normal random variables with mean and variance. Ex equal to mu x, ey equal to mu y. Variance of x is sigma x squared, variance of y is sigma y squared with correlation coefficient rho xy. Then the conditional mean and variance of y given x equal to little x is expected value of y given x equal to liter x and mu of x plus rho of xy times sigma y over sigma x times x minus mu of x. And this equal to mu of x plus covariance of x and y over sigma square of x times x minus mu of x. And the variance of y given x equal to liter x is sigma y squared times 1 minus rho of xy. Problem number 1. Let x and y be discrete random variables with Chorley distributors probability function fxy defined in the following table. Then calculate probability x plus y equal to 1, probability x equal to 0, and probability x less than y. So for the first question, to find probability of x plus y equal to 1, we basically find the pair that have x and y sum up to be 1. So x can be 1, y can be 0, or x can be 0 and y can be 1. So we have 2 points. And for the point x equal to 0 and y is 1, we have the probability is 1/9. And for the point x equal to 1 and y equal to 0, we have 1/6. So probability x plus y equal to 1 is f at the point 0, 1 plus f at the point 1, 0. And this is 1/9 plus 1/6. And the answer is 5/15. Question B. Probability x equals to 0. So probability x equals to 0, we basically sum this column, sum up this column. So we have 1/9 plus 0 plus 1/9. Probability x less than y, x less than y, so x can be -1, y 0, or x is -1, y is 1, or x is 0 and y is 1. When we add up these three probability, we got 5/15. So the answer is 5/15 for part C. Problem number 2. Suppose that f of xy is k times x squared plus y squared is a density function for the Chorley distribution of continuous random variables x and y defined over the unit square bounded by the points 0, 0, 0, 1, 1, 1, and 0, 1. Find k and find probability that x plus y greater or equal to 1. So first we need to find k, and remember one properties of the Chorley distribution function is this is continuous, so the double integral of this Chorley distribution should be equal to 1. And this is basic calculus, so we compute this double integrals. We got 2k/3 is the answer. So 2k/3 is equal to 1, so k is 3/2. And now we have k, so we have found the density distribution function. Now we need to find probability that x plus y is greater or equal to 1. And if you see here, the unit square bounded by these 4 points. So x go from 0 to 1 and y go from 0 to 1. So to find the probability, x plus y greater than 1, so that means y is greater than 1 minus x. So we are going to keep x fixed and write y depend on x. So x go from 0 to 1 and y go from 1 minus x to 1 because y is greater than 1 minus x. And work on this double integral, we got the answer is 3/4. An alternative way to work on this question is we use second type integral. So we are going to keep y fixed and write x in terms of y. So probability that x plus y is greater than 1 is y go from 0 to 1 and x go from 1 minus y to 1 because x here greater than 1 minus y. And also work on this integral, we got the same answer, 3/4. Here's the picture. So you see, if x plus y greater than 1, we basically find the area of the shaded area. So x, for the first type integral, x go from 0 to 1, but y go from 1 minus x to 1. By the second type integral, y go from 0 to 1 and x go from 1 minus y to 1. Problem number 3. Continuous random variables x and y have a Chern distribution with density function fxy is x squared plus xy over 3. X is restricted between 0 and 1. Y is restricted between 0 and 2. Find the conditional probability x greater than 1/2 given y is greater than 1/2. So here, remember for conditional probability that x greater than 1/2 given y is greater than 1/2 is probability that x and y are both greater than 1/2 over probability that y is greater than 1/2. So we need to find two things. The first thing is the numerator, which is probability that x is greater than 1/2 and y is greater than 1/2, and the denominator is probability that y alone is greater than 1/2. So here's a picture for the numerator probability. Y is greater than 1/2, but y should be less than 2, and x greater than 1/2 but less than 1. So the shaded rectangle is the area of the probability. And here's the picture for the denominator probability. Probability that y is greater than 1/2, so y go from 1/2 to 2 and x go from 0 to 1. So now first we find probability that x is greater than 1/2 and y is greater than 1/2. So we have integral from 1/2 to 1, 1/2 to 2 of the Chern distribution dy dx, because y goes from 1/2 to 2 and x goes from 1/2 to 1. And the answer for this probability is 43 over 64. Now we find probability that y is greater than 1/2, that is integral from 0 to 1, 1/2 to 2 of the Chern distribution dy dx, and the answer of this is 13 over 16. So the conditional probability is we divide the 43 over 64 over 13 over 16, and we got 43 over 52 is the answer. So one tip for you to deal with probability over two random variables is, for any question, please make sure that you draw the picture, because with a picture you can see clearly the recursion of x and y, so you're not going to be confused when you calculate the probability. Problem number 4. Let x and y be discrete random variables with Chern distributed probability distribution function of f of xy defined in the following table. Find expected value of x and y. So for this question, we basically multiply its value of x with its value of y and their corresponding probability. So we start with -1 and 1. So -1 times 1 times the probability 1 over 18 is the first pair. And similar, we continue to finish the table. So the next pair, -1 times 0 times 1, 9. The next pair, -1 times 1, 6, and until we finish the table. So the expected value is 1, 6. Problem number 5. Let x and y be discrete random variables with Chern distributed probability distribution function fxy defined in the following table. Find the marginal distribution of x. So to find the marginal distribution of x, we basically find the probability of x at the three possible values, -1, 0, and 1. So first, the marginal distribution of x at the point -1 is we basically add the third column together, and the answer is 1, 6. The marginal distribution of x at the point 0, we add the second column. And the marginal distribution of x at the point 1, we add the last column. So 1/3 is the answer for marginal distribution of x at the point -1. 2, 9 is the marginal distribution of x at the point 0, and 4, 9 is the marginal distribution of x at the point 1. Problem number 6. Continuous random variables x and y have a Chern distribution with density function fxy 3 times 2 minus 2x minus y over 2 in the region bounded by y equals to 0, x equals to 0, and y equals to 2 minus 2x. Find the density function for the marginal distribution of x for 0 less than x less than 1, and find probability that x greater than 1/2. So first thing first, should make the picture. Here we make the picture of first y equal to 0 is the x-axis, x equal to 0 is the y-axis, y equal to 2 minus 2x is this line, and we want to make sure that x is go from 0 to 1, and fortunately 2 minus 2x, the line y equal to 2 minus 2x crosses the x-axis at the point 1, 0. So here's the picture, and we need to find the marginal distribution of x. So the marginal distribution of x is basically we have to integrate the Chern distribution function respect to y, but y here you see that the range of y's go from 0 to 2 minus 2x. So the marginal distribution of x is we integrate from 0 to 2 minus 2x of the Chern distribution function. And we got the answer is 3 times 1 minus x whole square. This is the marginal distribution of x. Now we need to find probability that x is greater than 1/2. For this question, we have two methods. The first method is make use of the marginal distribution we have found and integrate from the interval from 1/2 to 1. And we got the answer is 1/8. Another solution is we ignore the marginal distribution function of y. What we need to do is integral the Chern distribution function for y go from 0 to 2 minus x, and x go from 1/2 to 1. 1/2 to 1. So thank you so much for watching. That's everything for today. I have 2 more lessons, and then I'm gonna finish SMP and probability preparation. Thank you so much, and hope to see you guys next video. Bye.